Welcome back to Chem 4300. In this video, we're going to begin Chapter 13 on the quantum mechanics of vibrational motion. Now, back in Chapter 5, we examined the classical mechanics of vibrational motion. And for small oscillations, we learned that the potential energy surface can be approximated as parabolic about some stable equilibrium point. This was what was called the harmonic oscillator approximation. Now, we also learned in that chapter that a system of coupled harmonic oscillators, for example, the vibrations of a polyatomic molecule, can be transformed into a system of uncoupled normal mode oscillations. Now, in Chapter 6, we examined the use of classical mechanics in the equipartition of energy theorem, and we saw that they failed to predict the correct room temperature heat capacities for diatomic and polyatomic molecules. That was one of the first clues that classical mechanics cannot be used to describe all kinds of motion at the atomic and molecular level. Now, in this chapter, we're going to see how quantum mechanics can be successfully applied to describe the vibrational motion and energies of diatomic and polyatomic molecules. So let's get started. So we're going to take the same simple approach that we did in looking at classical vibrations, and we're going to start with simple harmonic oscillation. Like here we have we're modeling the diatomic molecule as two masses connected by a spring, and we have that the kinetic energy there is just simply, as before, the momentum divided by 2 times the reduced mass, and the potential energy describing the force between these two masses, the force associated with this spring, is just 1/2 kappa F times x squared. Now, I've put hats on these guys because now we're going to use them as quantum mechanical operators, the kinetic energy operator and the potential energy operator. So let's take these and put them into the Schrodinger equation, which is H psi is equal to E psi. So for the Hamiltonian operator, we have the kinetic and potential energy operators. The kinetic energy operators here, notice we have the reduced mass there. And for the potential energy, we have 1/2 kappa F x squared. So this is the differential equation that we need to solve for vibrational motion of a diatomic molecule. Now, I'm going to do a substitution here. It's very common in solving this problem. I'm going to define k squared as 2 mu e over reduced Planck's constant squared. And I'm also going to define another quantity called alpha, which is going to be equal to the fourth root of the reduced mass times the force constant for the spring divided by the reduced Planck's constant squared. So in other words, alpha to the fourth is equal to that quantity there. Now, this quantity, this definition is something that's done in a lot of other textbooks. Sometimes they do it differently, so a little bit of warning there. If you see alpha in a harmonic oscillator, quantum harmonic oscillator problem in another textbook, be careful. They might have a different definition for alpha. So this is what I'm going to use. A few other books use that, but they vary from textbook to textbook. So with these definitions, this differential equation becomes this differential equation here. Okay. Now, what we're dealing with is a differential equation that's not as simple as the particle in the infinite well. So that case was very straightforward. We had sinusoidal solutions. We're not going to have such simple solutions in this case here. This potential energy that we're looking at goes to infinity, just like the infinite well, but it goes to infinity as x goes to plus or minus infinity. Okay, so it gets infinitely high as x increases to both sides there. Our wave function is going to have to be continuous and single valued over that entire range. So before in the infinite well, it was only continuous and single valued inside the well, and it was 0 outside the well. Here it has to be continuous and single valued over the whole range of values of x. So if you take a look at that differential equation that we have to solve, one thing you might notice is that when x gets really large, when we're getting way out there towards the ends there, that this term is going to dominate and be much bigger than this k squared term, which is going to be independent of position. So that means that at very large x, the solutions to this equation should look like solutions to this differential equation here. But that's only true at very large values of x. Solutions to this look like this. So there's simply some undetermined normalization constant, and then e to plus or minus alpha squared times x squared over 2. So this is either an exponential growth or an exponential decay. Well, of course, this is going to be going to, if x goes to infinity, this thing will go to infinity. That's not physically realistic. So we're only going to accept solutions with the negative sign in the exponent. These are going to be solutions that go to 0 when we get out to very large x. Now, again, these are not solutions to this equation. This is just solutions at very large values of x. But what this does is it actually gives us a suggestion how we might want to think about setting up this problem. And what we see is that this quantity, I'm going to use the Greek symbol xi, is alpha times x, might be a better way of reformulating the solutions to this problem. So instead of formulating in terms of x, we're going to formulate it in terms of xi, which is alpha times x. So if we transform this differential equation here, which is in terms of x, in terms of this xi, which is alpha times x, we get this differential equation right here. So I'm going to make a new wave function. Instead of psi, I'm going to use this chi here that is related by this relationship here. So I've just transformed this differential equation just sort of in light of the solution that it should have as x goes to very large values. So that's the solution we expect to have in the large x limit. And so what we're going to do is we're going to propose a solution where for all values of x, it will have this form where we've inserted this extra function, this h function, which will handle everything close to 0, where x equals 0. And we know that in the limit of xi goes out to infinity, it looks like this. But as we get further closer to 0, we have a solution where this h function will take over to give us the right shape. Okay, we haven't done much other than just propose the form of the solution where we just have this h function inside here. But if I take that solution and I plug it into this differential equation down here, then I can get this differential equation here. So I'll leave that as an exercise for you. Plug that into this, and you'll end up with this differential equation right here. And this is with this definition for n equal to k squared over alpha squared minus 1. Now again, I'm not expecting you to derive this and solve this equation. I'm just expecting you to follow the logic of how this equation gets solved. All right? Now, this equation here is something that if you go talk to one of your math major friends, they may say, hey, that's Hermite's differential equation. We already know the solutions. You can look them up. They're all tabulated. So at this point, what we've done is we've taken our differential equation that we started out in like the first slide, and we've slowly transformed it into a form where now it's recognized as a standard differential equation where the solutions are known. Or in this case, Hermite's differential equation, and its solutions are things called the Hermite polynomials. Now, for this solution to work, only solutions with integer values of this quantity n, which is defined here, are going to be physically acceptable. So we're going to have values of n equals 0, 1, 2. Those are the only ones that will work for the harmonic oscillator. So this is our differential equation. We can look it up and find the solutions of the Hermite polynomials. These are what these polynomials look like here. And here are some approximations for where the roots are, where those Hermite polynomials go to 0. Now, we're not going to be done until we normalize our wave function. So we have our Hermite polynomials. We can normalize this, and we'll get for the normalization factor here, this value here. And then if we calculate the energies, you'll find that the energies will be equal to the reduced Planck's constant times omega naught times n plus 1/2, where n is this quantity we'd had to define, where n is integer values of 0, 1, 2, 3, and so on. And this omega naught is something you should remember from the chapter on classical mechanics of vibrations, which is just the square root of the force constant divided by the reduced mass here. So what you see is that the energy levels are discrete. So the vibrational energy levels can only take on discrete values where we have this value of n going from 0, 1, 2, 3, and so on. the spacing between these energy levels, so if you took the difference between n and the next adjacent n value, the spacing between them will be h bar omega naught. In spectroscopy, sometimes, or oftentimes, people will talk about vibrational frequencies in terms of something called the spectroscopic wave number, which is just this omega divided by the constants 2 pi and the speed of light. So we'll come back to this here in a little bit. So here's what the energy level spacing looks like. So here is our potential energy surface that we had when we looked at this in the classical mechanics treatment. So here's the same potential energy function, but this is how the energies of the different eigenstates of the Hamiltonian are spaced on this energy level diagram. And one of the things you noticed here is that, I get a little note here, is that the lowest energy here in this picture is not 0. So 0 is down here. I had to put a 0, I should have put a 0 there. The lowest energy is a non-zero number. This is the 0-point energy. This is the same thing we saw in the particle in the infinite well, that the lowest energy state had a 0-point energy, and in this case, the 0-point energy is 1/2 h bar omega naught. So let's take a look at a simple calculation. Let's say we want to calculate the energy level spacing. So imagine this is the harmonic oscillator approximation for the quantized vibrations of a hydrogen molecule. What's the difference in the spacing here for the hydrogen molecule? So if we go back to, in the notes, in table 5.1 in the chapter, we saw that this wave number for a hydrogen molecule was 4401. This was measured spectroscopically. So what we can do is we can just take that relationship that I just gave you, and you can calculate the spacing for this hydrogen molecule just using E delta E is h bar omega, just like we saw before. We're going to multiply it times the, we're going to rearrange this expression for omega. We'll plug in our number here, and we're going to get a value of 87.423 zeptajoules, okay? Now that's probably not so, an energy scale that you're that familiar with, so let's try to make it a little bit more on the scale that makes sense to you. If you think about the equipartition of energy theorem, we learned that the energy likes to dissipate into all the different motion, and so vibrational motion, we expected to get a 1/2 kBt for the two quantities that were squared, the position squared and the momentum squared. So we expected kBt was the allocation of energy that should have gone to vibrational motion. But we realized in the chapter on equipartition of energy theorem that we didn't have enough thermal energy to populate these quantized energy levels. So let's take a look at how this difference in energy compares to what kBt is. So at 298, let's convert kBt to the equivalent of this number here, 4401, and compare it to the spacing. So if I take delta E is equal to h bar omega, and I plug in this expression that I did here, and now I'm going to set that equal to kBt, well, now I can calculate, I can rearrange this expression into this expression here, plug in my 298, and I can calculate that 298 Kelvin is associated with about 200 inverse wave numbers for this spacing. So in other words, 200 is how much energy is associated with kBt, but the spacing between the hydrogen's vibrational levels is 4400. So it's no wonder then that the room temperature heat capacities weren't able to populate these levels. They had only energies on the order of 200 inverse centimeters, and the energy gap between those hydrogen levels, vibrational levels, were 4400. So it wasn't until you got to much higher temperatures that you could start having enough energy to excite into these levels here. Okay, so let's go back to our wave function here, which we had written here before. And if I rewrite it back in terms of x, get rid of this xi, remember the relationship then, as xi is just alpha times x, then I can get this expression here. And again, I'll use a new normalization constant, which is just the square root of a alpha times this previous normalization constant. And the lowest energy wave function, the n equals 0 one, turns out to be just a simple Gaussian function here. So this is what we have for the n equals 0 function, and since when you multiply times this complex conjugate, you also get a probability distribution that is also Gaussian. And its standard deviation is 1 over alpha times the square root of 2. Now, before we look at those wave functions, I want you to remember back in the chapter on the classical mechanics of vibrational motion that we looked at this probability distribution of where the in our oscillator, where the mass was as it was oscillating, as in terms of the probability of looking at it and finding it at any particular position. And we saw that where it was passing through the zero, it had the zero potential and the maximum kinetic energy, so it was moving the fastest. We had the lowest probability. And out here at the turning points, where it goes out to the end and stops and turns around and starts to come back, these turning points is where it spent a lot more of its time, and that's where you had the highest probability of finding it. So we worked out that those turning points were related to the amount of energy that you had, and this is what we worked out in the classical treatment of vibrational motion. If I take the quantum result here for the energies, I can take these two results together, and I can find that the maximum excursion is related to this principal quantum number here. So this square root of 2n plus 1 tells me what the maximum value that you would predict based on the classical treatment of this problem. So this is what's called the classical turning point. And in quantum mechanics, that classical turning point would correspond to the square root of 2n plus 1 in the position here. So let's take a look at these wave functions, and we'll come back to that classical turning point here. So here are the wave functions. These are the n equals 0 wave functions, which I said were Gaussians. These are the wave function, and this is the probability, so the wave function squared. And then you can see that the n equals 1 here has one root here in the middle. It's at 0. That's a turning. That's a change in sign. And then we keep going out here. We have 2 roots to where it changes sign, and then we have 3, and we have 4. So it looks somewhat like the particle in the infinite well, but it tails out here at the ends, right? So it has this sort of kind of oscillations as you would expect. And of course, when you square them, you get very similar types of behavior here. But I want you to notice a few things here that are very different here. So again, for the nth oscillator, we have n nodes. So n equals 0 has no nodes, n equals 1 has 1 node, 2 has 2, and so on. It changes sign at the roots of those polynomials. So as I said, there's some differences and similarities with the infinite well. So the nth oscillator state corresponds to the n plus 1 infinite well state. So we start with n equals 0 here in the harmonic oscillator case. In the infinite well case, we start with n equals 1. And these arrows here, so I don't know if you can see this here in this picture, but I have arrows here that indicate the range that the classical oscillator would be displacing over. So this gray region here on the ends, that's what we call the forbidden region. That's the classically excluded region. So a classical harmonic oscillator would never go into this range here because they don't have enough energy to reach it. It's when you put in enough energy, the more energy you put in a harmonic oscillator, the greater further out that turning point goes. So for a fixed amount of energy, it can only go out to a certain point before it has to stop and come back in. And what you see is that in the quantum harmonic oscillator, the wave function extends into that region beyond the classical turning point. So in a way, it's tunneling into the barrier and showing up inside at positions where a classical harmonic oscillator would never make it to there. So this is a type of tunneling there that occurs, and we'll see this throughout all of the problems we're solving when we're looking at bound states, that the classical treatment of the problem, the particle, once its energy reaches the potential energy, the total energy reaches the potential energy, and there's no kinetic energy left, it stops and it has to go back. Here, it will reach a point where it's associated with a potential energy that matches its total energy, and then it will have a probability that extends beyond that a little bit. And that's this classically excluded region. Now, as we keep increasing n, eventually this probability distribution starts to come closer and closer to looking like what we see in the classical limit. So this is a case with n of 112, and you can see the probability distribution, and this gray line is the classical probability distribution that we calculated back in the earlier chapter, and you can see that slowly they're starting to look similar. So if you look back here, they don't look anything like that classical picture, but if you keep increasing n, then eventually it starts to get closer and closer to what the classical limit told us, classical mechanics told it what should be. So this is what's called approaching the classical limit. Now let me show you a few tricks for working with these Harmonic polynomials that will help you avoid some of the integrals that you might encounter as you're working through the problems in this chapter. So one thing you have to keep in mind is that these Harmonic polynomials with even values of n are even functions, and those with odd values of n are odd functions. And remember, when you're integrating an odd function over all values of positive and negative x, generally it goes to 0, right? And if it's an even function, then it will integrate to some kind of finite value. So let's look at calculating the expectation value for x for a harmonic oscillator wave function. So we're going to do our standard approach here. We make our sandwich here, and we apply our operator to our wave function, and we get back x times the product of the wave function times its complex conjugate. Now, in the harmonic oscillator case, all of our wave functions are real, so they're equal to their complex conjugate. And what we know is that, as I said up here, that since the wave function is even or odd, depending on whether n is even or odd, then when you calculate the product, if you take an even and an even, multiply them together, you always get an even function. If you multiply an odd and an odd together, you will always get an even function. So as long as we have n is the same here and here, we will always have an even function. And so we will get a function that will, when we multiply it times x, will always be odd. And so we get an integral that goes to 0. Okay, so this right here will always be even, but once we multiply it times x, we turn the integrand into an odd function, and so this will go to 0. Didn't do any work. I didn't plug in any wave function. I could tell right away that this integral was going to go to 0. Okay. Let's try that for the momentum operator. If I take the momentum operator, I create the sandwich here, I put in the form for the differential of the wave function, and what we know is that if you take the derivative of an odd function, you get back an even function. If you take the derivative of an even function, you get back an odd function. So here we have an integrand, which is the product of an even and an odd function, because whatever this one was, if this was even, then that's odd. If that was odd, then this is even, right? So thus, this integrand is an odd function. So if you integrate it over all values, it's going to come out to be 0. All right? Again, never plugged in a single wave function. We were just using what we know about the symmetry of these wave functions and their behavior, whether they're even or odd, to determine whether these expectation values are 0 or not. Okay. Now, another useful result that we'll use is that the integral of these Harmonic polynomials with this e to the I xi squared here is going to be equal to 0 unless m and n are equal to each other. So that's another great simplification, because anytime you bring together these Harmonic polynomials in the integrand with this form here, then we know right away whether it's non-zero or not. So we're going to use this here in a second. Another one that we're going to use is this recursive relationship, and I'll show you how to use these two recursive relationships. One is this one right here, which we'll come back to in a bit, and then this other one here involving the derivative. There's a recursive relationship for the different values of n. So this involves n plus 1, n, and n minus 1, and this recursive relationship involves n and n minus 1. All right, so just hold that thought. Let's look at some examples. So we're going to write and use the Harmonic polynomial recursion relationships to show what we already knew earlier, which is that the expectation value of x is 0. So we're going to just write down, since x is equivalent to xi, we're going to write down the wave function here. So now I'm going to use the wave function this form. So I have the wave function, the expectation value, and then I'm trying to calculate in the wave function. And then when you multiply it all out, you end up with the integral of hn psi hn, and then this e to the minus xi squared, okay? So I'm going to use the recursive relationship here, which tells us that xi times hn is equal to this. Now, so that's, okay, just to go back here real quick. I took this expression here, and I rearranged it to this expression here. So just check that. And once I have it in this form, then I can replace this term here in the integral, and that gives me this integral, which now breaks up into two integrals. And once I've broken up into two integrals, I see that this is an integral of the form that I talked about right here. And this one involves two different values of n, gone. And this one involves two different values of n, gone. So again, we get the same result that we knew from before, that the expectation value is 0. All right? So these are useful, and we'll use those later as we go through some of the homework problems in class. And so the last thing I want to talk about is polyatomic molecule vibrations. And so let's go back to where we were in the classical treatment of this problem. And we've already worked out all the details of how we can decouple those equations by doing a normal mode analysis. And when we were done, we had an energy expression which we could convert into a Hamiltonian, and it would look like this. So go back to chapter 5, look at that derivation of the normal mode energies for the polyatomic molecule, and you'll see that we just simply put hats on those normal mode coordinates, the time derivative and the normal mode coordinate there, and those are going to be our starting Hamiltonian for solving this problem. Now, I'm going to leave this as an exercise for you to show that the velocity of this normal mode coordinate, so in other words, q dot, is going to be equal to, the operator is going to be equal to minus I h bar, and then the partial with respect to qi. So that'll be one of the homework assignments to show that. But given that, we can transform this Hamiltonian into this form right here. Now what we've done is, now this is the kinetic energy part, this is the potential energy part, and we know this lambda here is the eigenvalues for diagonalizing the V matrix, the script V matrix we had in that chapter. And so you see now that this is just simply, since all these equations are decoupled, the sum of a 3n minus 6 individual Hamiltonians. So the total vibrational Hamiltonian is the sum of all these individual normal mode Hamiltonians, all of them inside here. So the total energy then is going to be obtained by using this total Hamiltonian, and h psi equals e psi, but the problem is going to be simpler because we're going to be working with individual normal mode Hamiltonians that will all sum up together to make the total Hamiltonian. Now one thing I forgot to mention here is that I dropped this VE because it's just a constant, and it won't change our solutions at all. It'll just be a number that we add to the total energy of the total Hamiltonian. So if we go back to that expression there, when you can write the Hamiltonian as a sum of decoupled Hamiltonians, in other words, the Q's in each one of these Hamiltonians are not affected by the other Q's, then we can take this Hamiltonian, which is this sum, and we can say that its solutions is going to be the total vibrational wave function for this total H is going to be a product of all the individual wave functions for each individual H over here. So this product, I'm going to use this big product symbol here. This capital pi means the product. It means multiply, psi 1 times psi 2 times psi 3 all the way up to 3n minus 6. So that's the total wave function, what it looks like, and what we're solving for now is all the individual problems. So once we have all of those solved, we can take all of their individual energies, add them up, and we'll get the total energy, which is associated with our total Hamiltonian. All right. So just to kind of summarize again, we're going to solve the Schrodinger equation for a polyatomic molecule, and it's going to involve solving 3n minus 6 Schrodinger equations or wave equations for each of the normal mode coordinates. And each one will be given by this expression here. So we've taken the big problem of all of the vibrational modes, and we now can just solve them for each normal mode independently, and then just add up all those energies to get the total energy, multiply all those wave functions to get the total wave function, and that's the solution. So it works out to be pretty simple. This is the only thing left to do, which is to solve that individual normal mode problem. But if you look at this, I'm going to do a little rearranging here. I'm going to rearrange it into this form. So you can check that you can rearrange it into this form. And then I'm going to define some new terms here. I'm going to define a ki squared, which is 2ei over reduced Planck's constant squared. That's this term. And then I'm going to define another alpha I. So this is for the ith normal mode, I'm going to define an alpha, which is lambda I over the reduced Planck's constant squared. And when I plug those definitions into this, I get this wave function, wave equation, and that's the same form that we had for the diatomic problem. So everything we just did with the Hermite polynomials, the quantized energy levels, everything we did before is exactly the same here. We're just switching from xi to q for this type of problem. So we're going to take this solution, this wave function, this wave equation here, and we can find the wave functions that satisfy this, and they're going to have this form here where we did this whole derivation from before, and here's the normalization constant. And now we have a vibrational quantum number for every normal mode that's present in the molecule. So the total energy then will be a sum of these individual energies. So each vibrational mode will be quantized, just like before, in terms of its energy, will be quantized as h bar omega I, where that's the normal mode oscillation frequency, ni plus half, where n is 0, 1, 2, where the frequency is the square root of that eigenvalue, and then the total is that sum there. And that's the solution for the polyatomic molecule vibration. So even though it looks complicated at the start, it boils down to a bunch of simple diatomic solutions that you just add up. So if you take the case, for example, for water molecule, this is what the energy levels for water, the first few energy levels for water molecule look like, and these are all calculated in the harmonic oscillator approximation. Then you see that this is what the 0-point energy is. So this is what we have: N1, N2, and N3. Those are the three normal mode quantum numbers here. So the ground state with N1, N2, and N3 all equal to 0 shows up right about there. And that has a energy of about, energy of about 8.9 times 10 to the minus 20 joules, or in terms of wave numbers, we're looking at about 4,500 here for that guy. And in this picture, this is the ground state. When we have multiple normal mode quantum numbers, whenever all of the quantum numbers are 0 except for one of the quantum numbers, and when that value is 1, then we call that the fundamental energy level. So in this picture here, all of them are 0 except for this one in the middle, N2. So that's a fundamental quantum fundamental energy level there. Likewise here, we have 1, 0, 0, that's a fundamental level, and then 0, 0, 1, that's a fundamental level. And these are levels where later we'll learn about transitions, and these will be the allowed transitions between the ground state and these fundamental levels. Overtone levels are ones where all of them are 0 except for 1, and that one value has a value that's greater than 1. So for example, here is 020 is an overtone level, 030 is an overtone level, and combination energy levels are ones with 2 or more non-zero quantum numbers. So for example, up here we have 110, that's a combination level. Okay. And so here we see the energy levels for the water molecule, and all of those guys, N1, N2, and 3, those energies add up, and so what we get for the ground state is we have the sum of all those guys, and so that's 4,500 is pretty high. Remember that that KT was about 200 at room temperature. KT was about 200 inverse centimeters, and you can see that these are quite big differences there, particularly with respect to the ground state and the first excited state compared to KT at room temperature. Okay, so that's going to be it for this lecture. In the next lecture, we're going to look at a slightly different topic related to quantum harmonic oscillators called creation and annihilation operators.